Be there on that side of the clicker.
Yeah.
Well, hello everyone. I'm Blake Hall. This is Colby Branch and Aaron Welby, and we're the baseball pitching machine team. So I'm actually on the MSOE baseball team here, and there are a couple of problems that I originally identified with our pitching machines. That being that they're really expensive, they lack the ability to quickly change pitch types, and they lack the ability to quickly reset after throwing a pitch. So we're spending a lot of money on our machines and not getting a lot of functionality out of them. So we're going to change that.
Our objectives and constraints for our project are that we would like our design to be able to impart spin on the ball in any of the lateral and vertical axes. We would also like the pitch reset time between each pitch to be no more than 7 seconds. This is to help emulate some real life batting situations. We also would like maintenance to occur no more than once a month, as Blake has experienced that maintenance on these current machines are kind of a hassle. So the constraints for our design are that we would like it to be controlled with an electronic controller, and then the operator can use a user-friendly interface to help change pitch types quickly. The power for our device will be using the standard 110 volt AC wall outlets and no secondary power sources. The budget for our functioning prototype will be $1,200.
So since we want to be able to accurately represent how these pitches move through the air, we first need to know what makes them move out of the standard machine and how they're getting their velocity, spin rate, and what's causing the break on the pitches over the distance from the mound to plate. And so they can spin along, when the pitcher's thrown, they can spin along 3 different axes, with really only 2 of them being important, those being the Y and Z axes versus the X axis, which we'll call the axis running from the pitcher to home plate. We're calling gyrospin, which would be similar to that being of a bullet or a football being thrown. And while gyrospin is used in when pitchers are throwing the ball itself, there's no use in the actual aerodynamics of having it besides just stabilizing it slightly. And so we're going to ignore the most part. But with spinning the other 2 axes, though, we get something called the Magnus effect is what we're going to mimic. And so the Magnus effect works similar to physics on like a airfoil, in that there's a low pressure side and a high pressure side. The low pressure side is instead though caused by movement than it is by the geometry of something. So this is fastball rotating perfectly backwards. And the top half of that baseball is rotating the same direction of the air relative to the baseball. The lower half is rotating in the direction relative to the air. That causes our low and high pressure regions. And with the baseball trying to move towards that low pressure region, it's going to not actually move up, but move down at a slower rate. The same principle can be applied to baseball spinning in any axis, causing it to drop slower, drop faster, break left, break right. So some of the pitches that we want to be able to mimic are fastballs, which have a high velocity, have almost direct backspin and very low gyro spin. Curveballs, they spin the opposite direction. Instead of spinning backwards, they spin over the top. They are significantly slower pitches, and they also drop faster than expected. And then there's changeups, which have a similar backspin to fastballs, but they also have a little bit of side spin that causes an inside run along with a bit of drop. So to do this, each of us made some designs, and we came up with 3 that we liked. This one's one of mine. It's I tried to make it as simplistic as possible, and it's a 2-wheel machine that primarily is using 80/20 to support it. But I built it with the ability for the 2 wheels and motors on the inside to rotate around 360 degrees. That way we can have one wheel spinning faster than another. and it will allow a more consistent, and that difference between the two wheels will be what determines the of the break of the pitch. With the player controlling and feeding the baseballs in, controlling the angle of each pitch to go along with it. This was partially inspired by a vibration dampener patent I found. While I'm not using it for its intended purpose at all, what I liked about it is that it gave me the idea to have a, they have a U shape. I decided just to make it circular, but they've made a device with the ability to rotate around one fixed axis, which is what we would need to deliver a baseball from the same point each time.
This is one of my designs. It is a 4-wheel. It is in this cross shape, and the 2 side wheels are kind of smaller, and they operate at individual RPMs so that you can control it. The point of that is to help create that spin by just using those 2 wheels instead of having all 4 wheels kind of operate independently. It is in this kind of like box shape, and it's got a front plate to help disguise what pitch type is coming out. That's to help the batter kind of emulate real game situations. I also have this control system for the feeding system. So it's going to take the feedback from a sensor of the wheels to know when it's at the desired RPMs. And then when it's at that desired RPMs, the system will then release a ball into the feeding machine. So it's based off of this article about this 4-roller mechanism. And this 4-roller mechanism helps create that gyro spin to throw the pitch called the gyro ball. And so the performance of this 4-wheel machine actually, compared to the standard 3-wheel machine, actually was much better. It would throw the balls at a higher velocity, it'd be more accurate, and it had the ability to throw that gyro ball. The biggest downside of the 4-wheel machine is that it is super expensive, so it kind of just negates that.
So this last design here is actually what we ended up selecting from our decision matrix. And it utilizes a stepper motor to drive a kind of rubber nub that creates an interference as the ball is traveling. So what we're doing here is creating spin with this rubber nub instead of by varying speed to the wheels. A normal machine typically works by speeding up a point on the ball by having one wheel spin faster than the rest. And this is just doing the opposite of that. It creates a friction that slows a point down on the ball. So what we're going to do is have 3 of these units with the stepper motor controlling a rubber nub, positioned 120 degrees apart, opposite from how a typical machine is set up, and we'll show that later. So we're just kind of doing the opposite of a normal machine here, and the hope is to make this cheaper than a normal machine, so we don't have to have very large motors with a lot of torque. And some of the inspiration for this came from this design right here. So this is pretty interesting. It has a chamber where there's 3 wheels that put spin on the baseball, but then it uses air pressure to launch it after that. So they were able to separate imparting spin on the ball from projecting it here. So we're hoping to kind of cut down on our costs and have more control over the spin by separating the 2.
So some of the criteria we used to determine and judge our designs for which was going to be the best was the cost, which was just the manufacturing, the prototyping, and the testing of our designs. The ball rotation degrees of freedom, which would be around that X, Y, or Z axis, how many axes we can throw spin along. The performance, that just kind of being how fast could we throw it, how accurate could it be, how much spin could we apply to the baseball. The complexity of it, how many moving parts do we have, along with the maintenance, how many moving parts can we kind of limit, or how can we make it as easy as possible to do maintenance for. And then the portability and usability, being how easy can it be to move and use the machine, assemble, disassemble if need be, anything required with that. And so then our decision matrix, we decided to weight the cost and the performance most heavily, as we wanted the pitching machine to be able to function as good as possible compared to our current machine, if not better, and then also keep that cost as low as possible. Of all of them, design 6, which Blake mentioned was the baseball interference design, scored the highest.
So in airsoft, they use these hop-up systems to kind of help ball flight. So what a hop-up system is this kind of base, small little system that is in the standard. And this is the standard version of the hop-ups. And so you got your barrel here, and then you got the feeder tube for the BBs. So this hop-up arm here is adjusted by a wheel, and it pushes into the little rubber bucking here. And so as the ball passes through, it squeezes the ball or the BB as it passes through, and it creates a backspin. And this backspin utilizes that Magnus effect, and it increases the ball BB flight time. And so as we can see how much, if you increase the interference by too much, it causes the BB to kind of fly straight up. But if you don't do enough, it'll kind of go straight down. So in our design, being able to affect how much interference will help us create as much break as we want. So this is a CAD model of our kind of our final design. It is going to use these kind of lead screws that are connected to the two mated gears, and then it's going to have a stepper motor to control it. We're going to have 3 of these assemblies placed 100 degrees apart. And so then we can then control each kind of assembly independently and then create the interference from each one separately. So this is kind of the orientation that we're going to have it in. And so as kind of Blake mentioned previously, a standard machine creates the spin by increasing the speed of one wheel higher or slower relative to the others. So in contrast, our design is going to kind of do the opposite effect of that. It's going to slow down the opposite side of the ball. And so, for example, if that top right wheel on the machine is spinning faster than the other one, it'll create this kind of top spin on the ball. And so on our design, we then create friction on this bottom left nub on the ball to impart that same spin direction on the ball. So as Blake mentioned, we designed our final design on design concept 6. And so design concept 6 in our final design uses this pre-made pitching machine. And then we will then mount that pop-up system onto the pre-made machine. And so doing this allows a majority of our budget to actually just go into developing our hop-up system. We don't have to spend money developing a way to project the ball as well. And so it helps reduce our complexity on the project as well as narrow the focus of it as well. Our final design will also be a scaled model, and the balls we'll be throwing are just foam practice golf balls. And then we'll also be using our hop-up system to create those different pitch types.
So Rapsodo is how we're gonna know what to tell our control system to do to create different pitches. So Rapsodo is a technology that the MSOE baseball team has access to, as well as most college and pro teams around the nation. So what it does, this is a camera sensor in between the pitcher and the batter, and it tracks the laces as the ball's coming in. So it's able to determine the velocity, spin rate. It can actually simulate the whole flight of the ball on the way in. So the important metrics that we're looking for from this would be velocity, true spin, and spin direction. So here's an example pitch from Rapsodo, and this is actually from one of our MSOE pitchers. Pretty good pitch, but we're looking at the velocity here. The true spin is the resultant spin rate minus the gyro spin, because we talked about how gyro spin doesn't actually create break on the ball. In spin direction, I'll talk more about that in a second, but horizontal break and vertical break. So we'll be able to validate if our ball is creating the spin that we want and how much it's breaking off this data. So spin direction, Rapsodo likes to represent this in hours and minutes. So if you could picture being the pitcher here throwing at the batter, the ball spinning in this direction breaks this direction. So this pitch would be a 5 o'clock spin direction. And what we're going to do is just convert this to degrees to be easier. So using this, we'll be able to break down the spin into components and tell our machine how we want the ball to spin. Some examples of spin direction. Rapsodo has a lot of average data on this. So we'll know what type of pitches we're wanting to create based off this. So for instance, if we want to throw a lefty curveball, that'd be a 5 o'clock spin direction as shown earlier. So we'll be able to validate off our results if we're getting the desired input that we want. And then as well as that, they have average data for people across the nation. So this is just one of our MSOE pitchers, his average data. If we want to, say create a pitch like Tyler Groner, we can do this. And Rapsodo has a lot of average data broken down by skill level on their website. So if we wanted to create a professional curveball, we could do that. College curveball, we can do that. So this is how we're going to tell our control system what to do. That's all we have. Thank you for listening. Are there any questions?
How about you guys first? You got any questions back there?
What's
You
that?
said that you guys are gonna use like the golf ball to like simulate and prove the concept. If the Rapsodo machine or data section focuses on where the seams are, how is it gonna on a golf ball, how is it gonna know what it's tracking?
Great question. So they also make Rapsodo for golf too. So I actually have a contact that I'm looking into at Rapsodo. Hopefully it's gonna let us use some of their technology for that. Otherwise, they have a unit that's around $300 that we can use to track our data if we need to do that. So we'll be able to do it for our scale model and actual baseballs.
What about you? Questions?
Oh, yeah.
I figured I'd let
And some
everybody else.
comments too.
Yep, that's absolutely perfect.
I thought, you know what, overall, you really good design process. You guys do. Overall, really good design process. I think one of the things I noticed right away, and it's always an issue, and so I always comment on it, are your design objectives. So if you go back to your slide there, let me pull it up. See, your design objectives aren't detailed enough. So when you go through this, when you start looking, you guys had a whole bunch of preliminary design, conceptual design, so you're following the design process correctly. You're actually doing that. So then the question comes up is what aspects of your design fulfill your objectives? So I think you could add more objectives to your objective list. So for example, like you talk about imparting spin. Okay, so I find it's kind of a general one. Are there actual numbers with this? And what do you mean about that? Is it velocity, direction? It sounds like later on you guys had a whole bunch of stuff.
Yeah.
You have like spin, you have spin rate, you have degrees of freedom. I mean, do you want any objectives on any of those?
We do have, most pitches spin typically in the 1700 to 2300 RPM range, so we're gonna try and mimic as close as we can as for a major league pitcher or a college pitcher would. We've left numbers off a lot of our stuff though, due to it being possibly a scale model. And with that, what that's causing is, since it's a different ball, there's different geometry and different kind of just effects with it. A lot of the numbers we're gonna be dealing with, it might be 2000 RPM for a baseball, but to get a similar effect on this smaller scale, it might be 4000, 1500 RPM, and we're gonna have to determine, or we're using the kind of relations between that to determine what we have, what's comparable, and what that would be on a full scale machine.
Yeah, so I want to add before you ask anything about that, we will have to validate that this is actually going to work with the real baseball too. So we're planning on designing an experiment where we create an interference just in one axis on an actual baseball. So we can kind of model, like if we create an interference at this much, how much it's going to break. So then hopefully we can compare that data to the data that we have with our model and see what we need to do on a real baseball.
But like I said, I think you still need these numbers, right? Because you need to know what you're shooting.
Yeah.
And so that's the point of the objectives. You have those models, those numbers there, so that you know what your designs are going to give you, or what you're shooting for. Objectives are design targets. And so when you want to hit that target, it's like, what target do you want to hit? So you need those numbers. So you answered my question, Colby. I mean, you say, I've got these numbers. We have these numbers. There's some issues about this, but they need to be here.
Okay.
Because that's what you're trying to shoot for. I think you clarified. I had a question about that nub. You're talking about the nub, but I think so it's on the diameter, right? I think
Yeah.
later on in the picture, you have three of them.
Yep,
And they're on the circumference and they run through the diameter.
yeah, so it was kind of difficult for us to explain that. I guess like we all have a really good idea of what it is. But Dr. Dudkowski here pointed out, we're kind of explaining as an interference. We're not really creating a pressure on the ball, we're just creating friction. So I hope that kind of makes
And you could turn any one of them on, so you got,
Yeah.
that's up 3.
Yeah,
And so basically, like if you wanna, you wanna slow it down on one
Mhm.
side. So what you would do is you would activate that
Yep.
one.
yeah.
And the other ones wouldn't be activated.
Well, we could probably have all of them activated at the same time, just at varying interferences is kind of the plan, so we can create that spin direction that we want.
And have you thought about how you're gonna control that?
Yeah, so we have our stepper motors with a kind of lead screw setup to just control the position of it.
You have a lead screw and maybe an actuator of some kind?
Yeah, just the stepper motor turns the screw to kind of, if you
Like
go
an
that side really quick.
electromagnetic
Yeah.
actuator, or you can,
Yeah, just that stepper motor will turn this gear that pushes this into it.
oh, okay.
We'll be able to vary, this is gonna be part of our testing, is varying the gear sizes and the gear ratios to determine how far of an angle gets how
You see,
far.
that's
Yeah.
an objective there, see, that's objective there, because that may not be the best design.
Yeah,
You could just put like a actuator.
we thought about that, right away. Could you go to the slide?
You need a lot of
666?
forces.
We were worried, we didn't really have a way to experimentally test if like an impact on this would break what we're using. So we actually used your power screw equations to
Oh,
calculate that at least, so we're confident that will work. But yeah, we thought of some other things, like using a straight up linear electric actuator, they're really expensive, so that's why we didn't do that. Maybe you have some more insight on that for us.
They, no, but they're really, really small and they're very good control. You get
Okay.
very good control, fine control on them. And the other thing, like I said, is then you can control each one independently.
Yeah,
So with a good, well-programmed control system, you can actually be running in each one independent of the other.
we'll have to have 3 of these setups so we can control them independently,
Yeah,
but
but I don't know, see, they also have, like, these systems, any system has a time delay to it,
Mhm.
right? So you send the signal, activate,
Mhm.
and that may be, enough, or you have enough delay that you're actually not controlling the ball like you think you are. Or you would like.
I mean, we're just gonna kind of set it before we send the ball through, so I'm hoping the delay won't be an issue there, if that makes sense. These are staying the same
Okay, so
spot.
There should be about 7 seconds.
Yeah, that's why we have. the-
Yeah, so they're just there once we set the pitch, but they'll change in between
So you would
pitches.
set it and then the ball's going through the.
So right now,
That might be okay.
yeah, on typical machine now, what you do is you just change the speed of each of the wheels, so you have to manually do that. And you're guessing at it, like you have to just keep changing them until you get the pitch that you want. So we're hoping with something like this with an automatic control, like you press a button and you do what you want.
Yeah. I can see that.
You have to do some correlation there too, right? Because you're gonna say, because like I think about the manual setup on the machine, what you're trying to do then is you're trying to eventually automate that. You
Yeah.
gotta model it
Yeah,
first and
absolutely.
come up with the right empirical model that says, okay, a good curveball is this many steps on this motor and this many steps on this motor, and then that's what you end up programming, but it's gonna take some repetitive, I'd say empirical modeling to get you to that. point.
Absolutely. So we have a really aggressive deadline on our prototyping because we need a lot of time to do that testing and modeling.
How are you gonna do that in the laboratory? How are you
Well,
gonna get that empirical relationship?
You gotta try to get that Rapsodo and try to
Yeah.
set it up in one of the
Or you
rooms.
do it that way?
Yeah.
But how do you relate it to the actual, it gives you all the information about the actual ball,
yeah,
the motion,
It's really
kinematics of the ball?
Do you
You
want to go
can-
back to that slide or the big table?
it'll even play like a video of the exact path and spin and everything of the ball, so it has like everything. There's even more than this too, put all on the slide.
That's
It's really-
really the exact, like kinematics of the ball itself.
Yeah, it models.
Well,
everything about
Be
it.
careful
Or
about
does it give you
that.
gross relationships of what's happening with the ball?
I think it's more that. I don't know that it gives you the exact kinematics. I'm not sure it's that sophisticated. I think that requires a little bit more research on your guys' part to
Okay.
see exactly what it gives you. It gives you spin rate and spin direction based on their interpretation of what spin direction is.
Yeah.
But then to me, one of the biggest things that is gonna have to come out of that, there is in two phases. It's how do you make the leap from golf ball to baseball? And getting the right information about, okay, does the spin rate and the spin direction tell you the same thing for the golf ball that it does with the baseball? And that is where I think, personally, I think we're gonna run into the biggest questions.
Absolutely.
Is at that early stage.
But my gut feeling is you got a lot of modeling issues. I think you're gonna have a lot of issues correlating what this is giving you to what's actually happening with that ball, especially when you're trying to trigger something, you're trying to set something, you put in input and you're trying to control that kick and that.
Yeah.
There's
You're
a,
gonna have a real difficult time. We really don't have the facilities here to get what you need.
I'll build it in my garage. I'll do that.
There you go.
My wife did say, what in the hell are you doing now?
and that's another reason why we're kind of focusing for the scope of this project is just imparting spin on it. We're not even worried about propelling it. So we have a commercial launcher that's just gonna shoot it into our kind of barrel unit. So hopefully that'll reduce the scope a little bit and make this doable.
Why you wanna use these golf balls?
Just because we didn't have enough money to do it for a full scale machine or anything, so.
Okay.
When I first proposed this project, Dr. Hart kind of mentioned, you know, you guys should probably do a scale model, and we all thought that was a good idea, so.
When you do the scale model, you gotta make sure you have similitude
I know.
between the scale model
And the ball,
actual-
and the ball.
Yeah.
Like, to me, like, I was thinking, even from the beginning, we've been kind of kicking this around. It's like, how does the golf ball compare scaled, scaled weight, scaled whatever, Reynolds numbers and things
Yeah,
like that, which is,
Exactly.
my brain's very tiny when it comes to that type of stuff. And it's like, but that's a big deal to me, is how well is it gonna scale?
Yeah, we absolutely need to validate this, and that's why I was kind of talking about making an experiment to kind of determine a correlation between interference and how much spin we put on it with the real baseball. And then hopefully that's kind of proportional to our golf ball data.
Yeah, I think that's a good place to start. Is it looking at, okay, if you think using a real baseball, does it do what you think it's gonna do by applying pressure to it? And then, because then you can say, okay, that's your proof of concept right there. And then you can work on, okay, the scale model, then are you getting, do the spin rates mean the same things? Are you getting the right spin rates? What does it do to your velocity and those types of things? But seeing if the pressure versus, I'll say, applied velocity, I know it's force, but applying the velocity to one side, does reducing the velocity on one side do what you think it's gonna do? That's gonna be a big.
But anyway.
Absolutely.
Yeah, sorry.
Yeah,
I'm going- Your time. We're on our time. Just having some food, learning about Cuba.
That's good. You guys gonna have some challenges though. I think we'll scale it up and.
All right, thank you, guys. I have a whole bunch of other stuff to talk to you about, but we can do that off. Nice job, guys. Thank you. Hello, Mohammed. How are you?
It's right there. So like, can I talk about the?
Get all weepy when I were my mechanics material correct. I know you weren't. You were in dynamics of systems. I'm teaching it again in the spring.
We're not in it. All right, well, if everybody's ready then.
Are you guys good?
Yeah.
Right, you good? All right, good afternoon, everybody. My name is Megan McKee. I am the team captain for the senior design team. Also involved on this team is Chase, Julian, and Sophia. So our design project is design a brace using a lattice structure and also do that with engineered foam padding. So in order for us to achieve this, we've split ourselves up into two sub-teams. So Julian and Sophia are focusing on the lattice structure of a brace itself, and Chase and I are focusing on the engineered foam padding. So to start off, I'm going to show you what a traditional brace is. So I'll hand this to you, Professor.
Thank you.
So a
It looks
traditional,
extremely uncomfortable.
exactly. So to start off, a traditional brace has two components. It's brace shell and then the foam padding. The brace shell is traditionally made of a hard polymer, and then the foam padding is just based off of experience of what orthotists have used so far. So the one you have in your hand right there and the one on the screen is called a Boston brace. It's a 3-point bending brace, and it's the most traditional brace used. This is because you can wear it under your clothes and it's not, seen really when you're out and about. These are normally used for, children, because that's when they notice scoliosis is when you're an adolescent. So one thing we want to change with this is to make the brace lighter and more comfortable for the patient, because children don't really want to wear that all the time if it's going to be heavy and make them really uncomfortable. So our problem statement is to design a 3D printed brace for these patients that have scoliosis that is lighter and more comfortable than the current medical braces that we have right there. And to achieve this, we're going to do a lattice structure design in the shell of the brace and within the foam that's being used. So I'm going to give a quick background on what scoliosis is. So scoliosis is considered an abnormal curvature of the spine that also involves twist in the vertebrae. The curve of the spine is determined by something called a Cobb angle. This is measured by the upper end vertebrae of the curve and then the lower end. And then between that, you get the Cobb angle. So there's 3 categories of it. So an angle from 0 to 25 is considered less severe. MDs just kind of watch and see if it gets worse. So there's no treatment for that besides just watching and seeing what happens. Cobb angle from 25 to 40 is considered moderately severe. So that is traditionally treated with a brace, whether it's a Boston brace or another type of brace, depending on what the MD prefers. And then the last category is a severe Cobb angle, which is anything over 40 degrees, which is traditionally treated with surgery. For this project, we're focusing on a Cobb angle in between 25 and 40 degrees, since that involves a brace.
Now for some background on lattice structure, as already mentioned, we're going to use lattice structure to lighten our brace, that it's not so heavy and it's more comfortable to wear for the patient. So lattice in general is a repeating geometry to lighten an already existing geometry by still keeping the overall shape. As you can see, there are roughly like 4 main geometries that lattice cells are made of. We have on the left a square shaped cell, an octagonal shaped cell, triangle shaped cell, and a hexagonal shaped cell. And by combining those shells on multiple, you're gonna get your overall geometry. So it's built up by many of those cells. So general lattice structure had its first appearance in the aerospace industry, and nowadays it is already used in industrial cases and already also in orthotics. And in general, lattice is gaining more and more importance due to decreasing cost by increasing availability. This is all achieved due to additive manufacturing. So as you can see, we have a lot of cavities in those cells, and by 3D printing, you only print the actual parts that you need of the cell, and the rest of the cell that doesn't have any material can be left empty. But that structure, the cells, each cell has like a complex geometry that is built up by different base geometries. I can show you that on the next page. So this is a square-shaped lattice cell, which can be made up by various parts, as you can see. So we have ball joints that can be used to combine all the different struts. And in general, we have outer vertical and horizontal beams that made up every lattice cell. And then combining thrust cells, angular beams, inner vertical beams, or horizontal beams, or inner thrust beams, you can design your lattice cell due to the requirement that you are having in your project. So the lattice cell that we are seeing here is like a full like a full build lattice cell, which is the strongest but also the heaviest. So when we are going for a very high stiffness, the low weight ratio, we are reducing our lattice structure. And as you already maybe know, the project that we're working on is an ongoing project for the last years, and the development and the choosing of the correct internal lattice structure has been done by the last year. So they have done a great job on that. And for the square shaped cell that we would use that we can use in our geometry, it would be an angular beam construction with inner truss beam combined. For the hexagonal square shaped, we would also have angular beams with vertical inner beams. And for the octagonal shaped lattice cell, we would have also angular beams with inner horizontal beams. As you already maybe have known, I'm missing the triangular lattice cell shape, the triangle shaped lattice cell. This is due to its higher, due to its lower stiffness to weight ratio. So for the brace that we're using, so for the base shell, we're only focusing on square shaped, octagonal shaped, and hexagonal shaped lattice structures.
All right, so a little bit of background on 3D printing, kind of what it is, what type of 3D printing we'll be doing. 3D printing is basically using a CNC machine to build up layers of material to meet complex geometry designs. What we'll be doing is using SLS 3D printing because for our engineered foam and for the brace, the SLS method doesn't need the support material to get the complex geometrical structure, which I'll pass that around to you now. So it doesn't need the support material to achieve that structure. Normally, if you look at that, you know, you're going to need a lot of support material. It's going to take a lot of extra time, cost a lot of extra, and you're going to have a lot of waste along with that. So to kind of remedy this, we've decided we'll be using the SLS printing method.
Now to our objective constraints of our project. So especially for the engineered foam, we have to achieve a stiffness of 348 newtons per millimeter, the tolerance of plus minus 20 newtons per millimeter. And the brace shell, whether it's made of nylon or polypropylene, has to be effective safety against yield of 2.73. And then we have also a tolerance of plus minus 0.5. For constraints, the weight reduction from the brace shell to the actual shell that we pass around has to be at least 30%. And as we already mentioned, we have to build this or manufacture this components by SLS 3D printing. For the material, we either have to use 3D Systems 912 or BASF polypropylene. And the lattice structure has to be conformed to the brace design. As you've seen, we have a lot of curvature in the brace, and our lattice structure cells have to conform to the outer geometry of our brace shell. So for the engineered foam that is passing out, we're using a TPU 88A, and now the last two. So the strut size of each cell can't be thinner than 1 millimeter. This is constrained by the additive manufacturing, so we can't print geometries less than 1 millimeter thickness. So we have to have at least 1 millimeter. And now a medical constraint, the holes that you see, especially in foam padding or any part of our brace that is going to touch the patient, can't be bigger than 10 millimeters. 10 millimeters is roughly like the diameter of this pen. Due to souring on the skin, you wear it, you're moving it, and by having big openings that are touching your skin, you have rough souring, which of course nobody wants to have. So we have to have holes in the lattice that are less than 10 millimeter diameter.
Now the brace shell team is going to talk to you guys more about the FAA analysis that they've done on both the materials that we've chosen.
So as you guys know, to make a good design, you need to have some sort of FEA analysis behind it so that you can go through and iterate on designs. For these lattice structures, we needed to go through and come up with validated models for the 3 different lattice structure types. that we're using in both polypropylene and nylon 12, as those are the materials that were chosen based off of current materials being used in the field. So we are validating these models based off of tensile tests. So we have these tensile test specimens and models for each of them, where we have fixed constraints on these two surfaces and a force pulling on these two surfaces to mimic a tensile testing machine from experimental data that was generated previously. We have deformations and loads to create a stiffness. We're using a stiffness because of the difficulty in figuring out how do we define stress? How do you define stress on this from a tensile test machine? It's not a material, it's a structure, right? So this stiffness parameter is what we're going to be using. We're looking for high stiffness for the brace shell. For the nylon 12 is a fairly linear material, so it was relatively easy to model. We put in the basic material properties for nylon 12 and it worked within a couple iterations. As you can see, we've got a % error against the experimental data of about all under 10% in terms of the stiffness. The polypropylene has given us a little bit more trouble. This data was gotten using a nonlinear model for the polypropylene. We used experimental data generated from just regular tensile tests of printed polypropylene for a stress strain curve to input into ANSYS. But we were getting these massive errors. And we're not entirely sure why. So our next step in trying to get a validated model for the polypropylene structures is to go through and retest, as we're concerned that there may be some issues, or may have been some issues in the printing or the testing of those specimens, because we were using a very similar or the same model in terms of boundary conditions as we did for the nylon 12 with polypropylene.
All right, now the engineering foam team is going to talk about the FBA analysis they have done so far. So I'll kick that off. All right, so in order for us to, do an FBA analysis based on we had given you, we had to compare it to testing that we've physically done. So the testing that was physically done was compression test, because the foam acting on the brace would be in compression. That's how they're going to treat the spine and, move it to where it's comfortable for the person to no longer have severe scoliosis or anything. So in order to do that, we had to mimic the compression test machine. So in order to do that, we had to do 4 types of boundary conditions. So we had the applied force going down in the Z direction. We had a frictionless support on the bottom of it, because that's how the plate is on the compression test. It's not a fully fixed support, it's frictionless. And then in order for the foam to squish properly in ANSYS, you have to have an X displacement and a Y displacement that are both equal to 0. That way, when you do it, it actually deforms in the Z direction, because that is what we're worried about, is how does it deform when it's pushed down. So in order to do the analysis on this, we went in between doing nonlinear and linear. So we first started off with doing a linear analysis, and ANSYS was having trouble running the material with that. Because the foam has the relaxation that's happening, ANSYS just couldn't properly mimic what was happening in the test. So we decided to switch to a linear approach. When we switched to the linear approach, we noticed that the deformation from the nonlinear to the linear didn't change at all. So if I had 20 newtons applied on top and the deformation in nonlinear was 0.002, the same thing happened in the linear when I did it. So that helped us kind of validate that we don't have to do this in nonlinear, and it'll be easier on the software and for us to be able to model more, because nonlinear took hours to run sometimes, and it didn't help us get anywhere too fast. So after we figured that out, the compression test that we did gave us our material properties. So it gave us an average Young's modulus of 2.86 for KSI, and then due to behavior foam, we use a Poisson's ratio of 0.1.
All right, so I'm gonna talk a little bit about our validation that we did. So in this table here, our goal value is the traditional soft foam, which you can feel inside of the brace there. That's 348 newtons per millimeter. Obviously, we were way above that with our compressive test foams. These were done by last year's group, and we wanted to validate the to make sure that we had all the materials properly modeled and that we were actually running our models correctly with how we would be testing them. So we had to first kind of do that. And so our actual results here gave us, you know, the medium foam was about 1512 newtons per millimeter. In our FEA, the firm foam was 2614, and then comparing these to those that are actually printed out, we got 1591 with the medium and 2620 with the firm. So we knew that we're in the general ballpark. So as I previously stated, obviously we're still way above with those two, the stiffnesses of where it needs to physically be. So our next step was to look at running stiffness tests in the FEA on different geometries to see how they would actually behave and react. So here we've got the square or the octagonal geometry first. That's the one that's in our first iteration of the foam. That's the stiffest one. And then a step down from that is the square geometry, which is less stiff, but still very far off. The hexagonal geometry, when we tried to run the FEA on it, it just completely exploded and blew up. But since we knew from previous testing that in general, the hexagonal geometry is close to the same stiffness as the square geometry, we knew it probably also was not going to be able to work for this foam. And then we have promising results with the triangular geometry, since all of the strut sizes for this foam FEA that we did, we had the strut size at 1.45 millimeters. So we still have the ability to decrease that and see if we can actually achieve the stiffness goal that we're looking for in the foam, since we'll still be above that 1 millimeter constraint in strut size.
So then our future work for next semester, each team has their own goals. So the ratio is going to create new polypropylene sample specimens to redo the tensile test to see if it was what could have gone wrong in the previous tests that were done, whether it was the printing directions changed or something just got read off the graph wrong or bad data was used. So they're going to look into that. Then they're going to validate those tests again with their FEA. And then after that, they're going to start printing lattice structure samples and then eventually finish with a total brace made out of the lattice structure. For the engineered foam team, we're going to run more FEA simulations to find the optimal geometry and strut size to get to a stiffness of 348 newtons per millimeter. And then after that, we're going to print samples and run those compression tests again to make sure our FEA is validated. And then once we do that, there is a plan to make the foam more comfortable. So the lattice structure geometry is going to be placed in like a sandwich method in between another layer of TPU 88UA on top and bottom to make it more comfortable on the patient. Because when we were talking to the doctor we're working with at Children's, if you guys felt that earlier, nobody would want that rubbing on their skin for a little bit. So once we find our optimal strut size geometry and we add in those sandwich components, we'll rerun FEA to find the optimal stiffness, since when we put those sandwich components in, it's going to increase our stiffness again. So we got to figure out what thickness those sheets should be. And then after both teams finish up their goals, we're going to finally put the brace together and implement it. So that is our plan and what we have done so far. Thank you all for listening. If you have any questions, we'll take them now.
I might have missed it, but are you trying to achieve a stiffness close to the traditional or higher?
Close to the traditional. The goal is to get it as close to the softest as we can, so the 348, because that is the foam that covers most of the brace. So when we were talking to the MD that we're working with, he was like, he wants that foam first, since that's mainly what you covered in, and then you can look at the foam later, the firm foam later, to get in those areas where you would need curvature correction.
And at this point with the brace shell, we're looking for a high stiffness to weight ratio so that we can reduce the weight while maintaining the same structural integrity.
Thank you.
Is that, and I'm sorry to explain it, but it kind of lost me a little bit. Is that 348 an actual number, or is that an FEA number?
That's an actual number. So
Okay.
orthotists gave us 3 samples of what they consider firm, what they consider medium, and what they consider soft foams.
Okay,
Those were all running compression tests, and then those were the average stiffnesses that came out of that.
okay, but the numbers that you're comparing to that actual 348
Mhm.
are FEA values,
Yes.
right? So there's like a, what I call a correlation gap between those
Yeah.
two. Like, how could you close that gap?
So what we'll have to do, once we think, we're close, because we had a lot of trouble initially with material properties just not wanting to work. Because initially we were running the FEA based off of different assumptions, and we were trying to do it non-linearly. And how the material behaves is that once you get to a certain point, it relaxes. And ANSYS doesn't like relaxation at all in its like modeling. So we were having a lot of trouble with that. But what we'll have to do is basically print out another test specimen once we think we've got the geometry right and compare it to the
Okay,
traditional foam.
okay, that makes a lot, that's kind of what I was hoping you would.
Yeah, we always want to, once we do the FEA simulations, we want to be able
Yeah.
to validate them.
Okay.
Now you have that 348 number, you put it 3 times in there, so I know it sticks in my mind. Otherwise, if it was just 3 different numbers, I wouldn't remember what they are.
Yeah.
But when you're looking at calculating error, shouldn't that be the base when you're calculating your error in there? Or should there be the FEA number that you got? You know what I'm talking about when you're calculating the error? If you go back to that slide. So if you have, like here, okay. 1094 will have much larger error than 588, which does in there. But if you go compared to 348, it'll be even much higher, because now I guess you're taking 1094 minus 348,
Mhm.
then you're dividing it by what? 348?
Yeah.
In every one of those cases?
Yes.
Then then you're right. Then my calculations are right there. So 2614, roughly I could go, yeah, that 200, that it makes sense. A good point.
I had a question about the stiffness of the brace itself. So you're looking at the stiffness in a pull test, right? Compared, and are you comparing it to the pull test stiffness of whatever that material is?
So, yes and no.
Okay,
We're using the stiffnesses of these. The stiffness is really a metric to compare each lattice to the other lattices.
okay,
The actual test of whether or not it works with the brace is going to have more to do with when we go and model the full brace shell,
Okay.
which we will be doing. Because the forces, stresses, strains, all of that are very complex
right,
when it comes to the brace, with the geometry and, people moving around like this. So we don't have a good way to do a one-to-one comparison
Right.
at this point. So we're gonna be taking whichever one we find to be, or have the highest stiffness to weight ratio, and implementing it onto a brace and working from there.
gotcha. Because that was actually the end point of my question was I was thinking about, that's a complex load case. You've got bending stiffness, you've got torsional stiffness, you've got all of that going on. And my I was thinking in my head, well, how do I know my lattice, which is gonna be somewhat anisotropic, and that solid material somewhat anisotropic? How am I gonna know that my lattice brace is gonna have the same
Yeah.
torsional stiffness or bending stiffness as that bit will? That's where I'm.
That's where those, you're testing.
Yeah, so at the end of our design, we're gonna test our printed brace. And we don't have a showcase here, but the brace will not be fully made of lattice structure, so it's not like the TP, the foam prints. We still have solid parts
Okay,
where we have very high load, for example.
gotcha, okay.
And we implement some area, I don't know, I would say 50 to 70% maybe of the actual brace will be made of lattice. The rest will be still solid material. And then Professor Rizzo has testing device already downstairs.
Cool.
That, yeah, I'm gonna take care of as part of my thesis. I do thesis. But we're gonna test different braces and also the printed brace and compare them to the actual brace and a few different other brace designs that are already existing.
Very cool. And was it 30% overall weight reduction is your target
For the brace shell.
for the shell?
For the shell itself,
Okay.
yes.
That wasn't for overall, right?
So we try to achieve, so the weight reduction is for the overall, for only the pressure, for the hard plastic, and then for the foam, we will see what kind of weight reduction or if we get a weight reduction. But
You talked about, did you call this 3-point something?
Yeah, it's called 3-point bending.
Okay, where is that 3-point bending coming from? What is it talking about?
It's the curve up there.
Yeah. Okay, so you don't have, let's see if I remember this, so, all right. So if you have, sure, that's a curve, why not? All right, so the 3-point bending is pretty much for, a Boston brace, so this one's gonna be 3-point bending. The way it does this is by using basically just horizontal, focuses. So that's a terrible curve, hang on,
Yeah, I think it's more cool.
that's bad, let's just don't see it.
Curve.
Let's do
Yeah, there
that.
you go.
Yeah, no,
Okay.
really. So you'll have, force here that's pushing on that curve to bring it back into center. This is where your spine is close to the line.
Yeah.
Then you'll have reaction forces going the other way to even that out. So
And top ones.
is it the other,
Yeah.
they are in the same direction?
Yeah.
Yeah, right. So you'll have that to push it back the other way. You know, so that's how like the 3-point bending brace. And then there is one called the 4-point bending brace, which is called the Milwaukee brace. So that one involves a chin strap, so it's a little less wanted for children, because if I was a child now to walk around with a brace and a chin strap, I would not leave my house. So this one's going to be the Milwaukee brace. Okay. That one's 4-point bending, so it has, gonna have vertical force. Yes. And then it has,
It's effectively the spine in tension with the
Yeah.
same 3-point bending.
yeah, it does that, and then there's another horizontal curve somewhere in here. I can't think of it.
But you have Boston.
Yes, it's the
Oh,
same as the
great.
Boston with the tension. pattern.
Yeah. But it's called 4-point bending, yes.
The way that the brace actually applies that force, when you're designing the shape of the brace, you use a scan of the patient. The patient is put in an apparatus where there are, the 3-point bending is applied using straps to straighten the spine.
It's called the rack.
Well, some people do that. That's actually, that's what's done at Children's here.
Okay.
And that's
So-
proprietary to there. It's their technology.
But then a
Not everybody
scan
does
of
that.
the torso geometry at that point with it in the right, with the spine in close to. So that's not actually the shape of
That
the torso.
This is that condition, so it's. This is then wherever you apply the load, that's gonna be 3-point load.
Yeah.
So depending where the curvature is, where how you wanna correct things, I can move that. Is that right?
Yeah.
Does that,
Because
location of the application of load changes so that it's adjusted?
from the design of the brace, they apply, a lateral load. It's actually not in a plane like shown like that. It's a simplification of it. And so you generate a 3-point bend.
So wherever it's the narrows, they are pushing it in there, I see.
Wherever the apex of the C curve is. From that one, it's hard to tell. The problem with the Boston brace is they basically have a cylinder, and then the padding inside is what's actually generating the curve. So you gotta look on the inside of that. Wherever the padding is, that's your
That's
apex
faster
of the
than,
curve.
should pretty much that's it.
That's the apex of the curve.
That's where the load is.
So that's not, yeah, it'll be on that side. It's like that's on your left side.
One final question for me. For the brace, I believe, correct me if I'm wrong here, you mentioned that you're using polypropylene and nylon 12 for the brace material. How did you guys come across to use those materials, or how did you determine that other materials wouldn't be suitable for this?
So that was largely from previous research that had been done by other groups. Looking at the properties of the materials, the ability for the materials to be machined, because the doctor will do adjustments later, and its toughness.
Alright.
I also want to add to that, the MDs really like polypropylene, so they wanted it out of that. But one of the issues is it might not always be like readily available when they need a brace. So as a backup, since nylon 12 is a little more readily available, we want to make sure it works in both with both materials.
Alright, thank you.
I have a question. So as far as the scope of your project, I heard that you're wanting to reduce the weight. Are there any other kind of design changes that you want to make to this? Or are you just trying to mimic this brace using additive manufacturing?
So we want to make our engineered foam like actually feel comfortable against the skin, because if you run your hand across that, it's kind of rough.
Yeah.
And kids are wearing these for 20-something hours a day. And if you've got to wear that for 20-something hours a day and you're moving around and running around and playing,
You're taking it off.
you're
Yeah.
not gonna have a good day.
Yeah.
So we want to kind of make the engineered foam more comfortable for the patient to wear.
And then on like the shell, like that design, that's, each patient is gonna be different, so it's gonna have to, like, if we were to design one for that, the bending points will have to be the same because that's where the curvature is, but it will be made lighter, and then, you know, you go to a different patient, they'll have a different curvature, and you'll have to redesign it for that.
The end result of what we're looking for is to improve patient compliance. One of the biggest issues with these braces is that your average 12-year-old is going to go into the bathroom during lunch and take it off, which, yeah. And that allows the deformity to progress and get worse to the point where they end up requiring surgery.
Nice job.
Nice job, yeah.
Oh. My sister-in-law wore both of those braces as a kid, the Boston and the Milwaukee. And as she got older, her scoliosis came back and her cob angle got to over 80 degrees. And
That's
that,
really high.
that was 3 16-inch titanium rods at age 60. Having those installed, that was she's not a happy camper.
Yeah, it's.
Yeah, she showed me the X-ray.
They look like video.
Honestly,
So
pretty much are.
How many feet did she gain?
Yeah, she got taller when they straightened her out.
Go from like